Thank you. So I moved to New York last year, and I work as a software developer at 2 Sigma, which is an investment manager amongst other things, doing lots of open source there. Most of you probably know me from working on the pandas project, which will have its 9th birthday in April. We've been planning a lot of development work in pandas to renovate the internals and take advantage of modern hardware over the last year. So if that's something you're interested in, feel free to reach out and get in touch with us, on the mailing list or on GitHub in the community. I've gotten involved in a couple of Apache projects, Patchy Arrow and Apache Parquet, over the last year, and I'll talk a bit about those today. Have a number of other Python projects. I've worked a number of places. I was a startup founder for a while. But there's a consistent theme in my work, which is that I'm very concerned with how to make data analysis faster and easier. So faster, in terms of people time, but also in terms of computational time. And these things are often very closely related, that the code that you write, it's no fun if you write nice looking code, but you press return, and then you have to go and get coffee while the code runs. And so if you can make that interactive experience of working with the data better, that will make you a good deal more productive, and that we can also move on to build higher level analysis tools on top of that strong foundation. So mandatory legal disclaimer, since I work for an investment advisor, you can read that when I publish the slide deck. So what this talk is about is to talk about PySpark's performance and why some parts of the library are slow. Approaches that you can use to make PySpark faster, and specifically work that we're doing right now, and we've been planning, and I gave a talk about this at SPARC Summit last June. And at that point, this work was a bit of a twinkle in my eye, because we needed to build the core technology that would enable us to do this integration work into SPARC. And so I'm very excited to have some real hard results to show you today. I'll talk a little bit about the work that is upcoming and ways that you can get involved and help make the Python experience on SPARC even better. So as you all know, SPARC is largely implemented in Scala. The core of the engine is implemented in Scala and runs on the JVM. There are Python and R APIs, but what they are primarily doing is manipulating data structures and objects that are living in the JVM. So when you write a PySpark instruction or you write a SPARC-R instruction, it's sending a message to the SPARC driver to change an RTD in a certain way, or manipulate a data structure in a certain way. And so there's lots of workloads in SPARC where you can use Python and R purely as a scripting front end, because you don't want to compile anything, you just want to write interpreted code, fire up a Jupyter notebook, and get up and running really quick and try something out. And this is the same reason why Python and R have become popular programming languages in the first place, because of that immediacy, the ability to really quickly and interactively build data analysis. But when you use SPARC like that, you aren't actually running any Python code. You're manipulating objects in the JVM, you're sending instructions to the SPARC driver. But if you have custom code that is written in Python that uses pandas or uses scikit-learn or NumPy, one of the analysis libraries, at that point you get into a different part of the PySpark project where there are some performance issues. And so you may remember when SPARC Dataframes were announced, it looks like this was at the beginning of 2015, so this was SPARC Summit East 2 years ago. And when this was announced, this performance benchmark was shown comparing the performance of Python data frames and Scala data frames. And the performance is aggregating 10 million integer pairs. And this is really great, but it's important when you look at a benchmark like this to understand what is being compared. So SPARC data frames are a perfect example of using Python as a scripting front end for the JVM. So when you are writing data frame operations, what you're really doing is building an SQL query plan inside the SPARC engine. And so when you go to evaluate that, you aren't actually running Python code, you're running a SPARC SQL query plan. Now when you get into writing custom code using RTD.map or registering custom UDFs with SPARC SQL, that's a slightly different business, and I'm going to talk more about that. So if you think about SPARC data frames, so here's a canonical SPARC data frames example. We have a user's data frame. We filter the age column, group by gender, and call count. And so if you were using pandas, this is, with the exception of that capital B, which I will forgive the SPARC team for, it is, this would be valid pandas code. So this is great because this is scalable, could run on 10 billion rows, 100 billion rows, whatever size data set you're able to process in SPARC SQL, and this is Python code that you can run from a Jupyter notebook. But if you think about SQL, this statement is equivalent to the SQL query. So select gender, count star, filter, group by. Internally, it builds something it builds an intermediate representation of the query, which is an aggregation with a predicate and some metrics and some group by clauses. So there are many kinds of workloads where it cannot be completely translated into SQL, particularly when you have custom extension code in Python, libraries which are written in Python that are far too complex for, that can't be compiled into SQL, or that make assumptions about the residency of the data. Like a lot of the code that you write in Python assumes that the data is in memory. So the two key ways where SPARC, the Scala part of SPARC interacts with Python is pushing and pulling data sets to and from the SPARC driver and running custom Python code, which I typically call UDFs, user-defined functions. So if you look into the internals of how a Lambda function works I'm sure you've used PySpark, you've written PySpark code, and you write RTD map, lambda x, whatever, you write RTD filter, lambda, and so forth. If you're wondering how that works, and you dig down into the Python RTD.Scala, the SPARC driver spawns a pool of child worker processes, which are fully formed Python interpreters, and it sends them a stream of instructions and data, including not only the data set, which has been serialized out of the SPARC driver, but pickled, serialized functions. So when you write the code in Python, that function gets pickled and sent to the SPARC driver, broadcast around the cluster. And so when the worker process receives that stream of data, it says, OK, I've got a function to evaluate on this data set. Let me unpickle that. And now let me unserialize the data set and run that Python function on it. And so you can look in Python RTD.Scala and see that a lot of the machinery of that code. And so if you think about the UDF problem and the other major area where Python interacts, in-memory Python interacts with SPARC, pushing and pulling data, it's a very similar problem because the SPARC driver is making data available to the memory space of the Python process. So the Python interpreter, it's written in C, it has extensions, a lot of C extensions, C++ extensions. So somehow you have to get that data into the same memory space where the Python interpreter is running to evaluate your code on it. And so the way that the data is getting sent through a Unix socket, and then it gets converted on the Python side. So there's some issues with this. One of them is the efficiency of how the data is being marshaled between the two processes. Another one, which I don't have time to go into detail today, is the computation model. So namely, it is using, in large part, Python as thinking about scalar values, so a single Python string, a single Python float, single Python integer. And so when you receive that stream of data from Python, you're having to construct individual scalar Python objects. So it's different from, if you've used pandas, you've used NumPy, you're used to working with whole arrays of data. You might have a 100 megabyte array or a gigabyte array, but internally you're manipulating a data structure that is in C and algorithms that are written in C. And so there's none of this kind of boxing overhead or scalar computation. And when you work in that way, you introduce a lot of overhead from the Python interpreter. When you're using pandas and using NumPy, you don't have that overhead. So it would be really nice if, rather than saying, data frame map foo, where we get one row from a data frame at a time, that instead we have a map pandas function. And I put an underscore because I really like underscores. But where you write map pandas, and the semantics of the function that you write is that you receive a data frame and you return either a series or a data frame. And so your computation model is vectorized, it's batch-oriented. You can use NumPy pandas, kind of all the nice things that we have in Python. So this leads me to talk about a project I've been working very hard on over the last little over a year, called Patchy Arrow. So at the end of 2015, beginning of 2016, I was investigating ways to connect Python more efficiently to SPARC, to Impala, to different big data systems. I had started building Parquet file support in Python. I said, well, I read the Parquet data, but where do I put it? Pandas, NumPy doesn't have support for nested data, a number of things that are found in Parquet. And so in multiple areas, I was seeing this need for an intermediate, column-oriented data representation that could be used in many different projects. And as I talked around and reached out to different people in the open source community, I found that this was a problem that many people had dealt with, having a common memory representation that they can move around efficiently between systems that's column-oriented, because a lot of things these days are column-oriented. So you can move data around efficiently, and once you have that data in memory, the way that the bytes are arranged in RAM is suitable for very fast, efficient computation. So these days, taking advantage of modern hardware, GPUs, CPU intrinsics, we'd like to be able to put this data on the GPU and do parallel computation on it, or take advantage of SIMD instructions in modern CPU architectures. So Patchy Arrow was a collaboration born out of this shared need for moving data around fast and being able to process it really fast in memory. And so if I think back on the last 10 years of writing Python code, I think about all of the different data converters that I have built over the years. CSV writers and readers, database connectors, converting from different file formats, serialization formats, and as you add more systems to the problem, you end up with this n-choose-2, combinatorial explosion of data connectors, where you've got to build a custom connector between every system. And so for me, one of the main benefits that I reap from a tool like Arrow is that we have a common memory representation, metadata, schemas. It may not be for any given pair of systems, there might be a faster way. But at least this is a fast way that we know is fast. And if two systems can speak Arrow to each other, then at least we know they can handshake at that level, and we don't need to write a custom connector. And so that will save everyone a lot of time. So if you go down kind of to the lowest level of, what does Arrow give you? So when I'm thinking about the Python problem and I want to create pandas data frames as fast as possible, so I want to receive a byte stream from SPARC, for whoever is giving me data. And I want to be able to construct a table that references that byte stream without doing any memory copying. So when you're thinking about serialization and file formats, it's memory copying that completely kills your performance. And so zero copy is completely essential. And so when I receive a payload of Arrow data from a system, I can look at the schema and I can extract any single value in that data set in constant time. So that abstraction and the ability to reference an arbitrary byte stream and do random access on any value in the data set is very, very powerful. On top of that, we've layered a messaging system, which I'll talk more about, which we can push data over the wire at very high speed. And we can represent data that is fairly complex. So if you have nested JSON data, assuming you have the ability to infer the schema of the data, which might include data structures like lists and unions, because sometimes you see a bunch of integers and then you see a string just to make things fun. So you can represent union structs, lists, complex types in the schemas. And over the last year, we've been working really hard to have compatible implementations that are accessible in Java and C++ and Python. So the wire formats are where things really get interesting when you're thinking about SPARC interoperability. So initially, we created what I will call a random access file representation. And these are bytes that you send through a socket, and you say, OK, this is arrow data, and then the receiver gets a stream of bytes. And it will look, and then the random access file looks at the end of the file, and it sees a metadata payload which describes the entire structure of the byte stream. And from there, you can say, OK, well, I'm a table with 10 columns, and here are my column types. And now you can construct a data frame very fast. The parallel to that, which we just added to the project in the last few weeks, is a streaming file format where you don't necessarily know how much data you're sending, but you can send the schema, which you know up front, and then start sending chunks of data. And a chunk of a table in Arrow is called a record batch. And so it might be 100 rows, it could be 1,000,000 rows. But each record batch is fully encapsulated. It has its own metadata describing the individual kind of memory layout of the record batch. So one of the exciting outcomes of the streaming format, and I did this analysis on my blog, is taking, and so the benchmark that I did, I took a gigabyte of data in a pandas data frame and said, what happens if I break this into progressively smaller streaming chunks? Because one of the conflicts you run into with columnar data is that a lot of data is stored in row-oriented, record-oriented format. And so the cost of transposing to column-oriented could be quite high. But I found that even breaking the data into chunks that are 256K in size, that I was able to get over 5 gigabytes a second bandwidth converting to a pandas data frame. Now, if you make the chunks really small, around 16K, so that's a really small amount of data, your performance starts to degrade because the memory access patterns become more inefficient. The API for interacting with this, Python, very simple. Open a stream, read the arrow table, convert to pandas. Very simple. So once all of this machinery was built, we collaborated with one of my colleagues from 2 Sigma, some fine folks from IBM, which was very excited to get involved in this. It's SPARC 13.534. And what we did was we looked at 2 pandas. When you call SPARC data frame 2 pandas, it's fairly slow. And we looked at the data serialization and said, OK, how can we integrate Arrow and use that for the data transfer and see what that would do to the 2 pandas performance. And the test case that I'm going to show you, I generated a Parquet file which once decoded into memory is 128 megabytes. It has 8 columns. They're all numbers. The package to do it is on Conda Forge. So if you use Conda. So here's the test case. We create a SQL context in PySpark. We do some caching to make sure that SPARC reads the Parquet file, pulls the data into memory. And then I call 2 pandas a few times. And I'm using the cProfiler integration in Jupyter Notebook to capture profiler output from those calls. So calling this function 5 times, and I spend so much of my life looking at cProfile output, so I'll explain what's going on here. So in overall, it took 62 seconds to transfer the data frame 5 times, so a little over 12 seconds per transfer. That's around 10 megabytes per second, which is not very fast. And if you look at what's going on here, if you see the socket.py business, about 7.5 seconds is spent in I/O, and so that's SPARC collecting all of the data as internal rows and then sending the data over the wire. And all of the rest of the time is spent converting those internal rows in Python into a pandas data frame. And you can see at the bottom, there's the data frame.from records, which creates the data frame. So using it with the current patch, we have pull request we have open with SPARC that uses Patchy Arrow and does the conversion on the SPARC side into Arrow binary format. We went from 62 seconds down to about 9.5 seconds. But if you look at the breakdown of where the time is spent, in the I/O, about 9.3 seconds was spent in I/O, and a very small amount of time was spent converting from the Arrow format into a pandas data frame. So to summarize, if we look at just strictly the I/O, we went from 7.4 seconds to 9.3. So the I/O got a little bit slower because we're doing more work in SPARC. But the conversion to pandas became much, much faster. I'll tell you exactly. I'll divide one by the other and tell you how much faster. Perhaps more interesting metric in terms of your SPARC job not failing is the memory use. There's a very nice tool in Python called Memory Profiler, which takes samples of the process heap to give you an idea of the peak memory use when you run an operation. So even though this is 128 megabytes of data, I found that when I run 2 pandas, that the peak memory use is approximately 8 times the size of the data set. And if you know about Python objects, you know that the overhead of even a single floating point value can be in the order of 6 to 8 times the 8 bytes that it takes to represent a float in memory. When we used Arrow, that memory use went from about 1 gigabyte to about 256 megabytes, which, given the design of the project, is exactly what you would expect. We receive a byte stream, which is about 128 megabytes. I create a pandas data frame, and then I move the data into the data frame, and then I garbage collect the Arrow stream. So you wouldn't expect, if you've done your homework and done things properly, 2x is the best that we can hope for with this architecture. But if you break down the performance, in the current 2pandas implementation, the deserialization in Python is almost 90% of the runtime. And when you talk about data serialization, people often quote, well, data serialization accounts for 80 to 90% of the runtime of applications. And here we have concrete proof of where that is the case. I would argue that the memory use is actually more concerning in terms of running out of memory in Python is a showstopper. So to the extent that you can avoid memory errors, might be that your code takes longer, but you don't want to run out of memory. But in the Arrow version, the deserialization to Python takes about 1% of the time. So we went from almost 90% to 1%. The cost of that is that the time for SPARC to prepare and send the payload is about 25% higher. And the memory use is a big deal there. So this is all to say that this is a nice way to get access to data that's coming from SPARC. If you have a large data set that is the output of a SPARC job, it can be more efficient to write that data set to HDFS or to some persistent place and then read that data directly into Python from HDFS or from S3. So in parallel, a thing that I've been involved with is building a native Parquet interface in Python. So if we compare the performance of here, we have 128 megabytes of, where did I put the performance numbers? To read 128 megs of data using 2pandas with this patch in SPARC takes 1.9 seconds, but from disk, we can read the Parquet file about 10 times faster. So that's in excess of 1 gigabyte per second. So if you're really interested, one thing I found intriguing when I did this analysis is why does it take SPARC 25% more time to produce the payload that's sent to Python? So I dug into that. And the code that sends the data to Python, the results of the SPARC SQL instruction are assembled in memory on the driver in an array of internal row objects. And it's that array of internal rows which is then converted into Arrow format and sent over the wire. I dug further and broke down that performance and found that about 75% of the time was spent preparing an in-memory Scala array of internal rows, and then about 20% of the time was spent in a single thread that converts those internal rows into Arrow format. So one possibly obvious thing we can do is rather than collecting all of the data from the task executors on a single node and doing the conversion, we could perform the arrow conversion in parallel on the task executors, and then have those task executors send serialized arrow record batches back to the driver, and those can be sent out in streaming format to the Python process. And I was really excited that yesterday, so Brian from IBM started a patch to do exactly this, and this performs a parallel conversion of the data frame on the task executors, and was able to get in a small patch about a 40% performance improvement. So I think we've really just scratched the surface in terms of what we can what we can accomplish with this technology, and so I'm very, very, very excited about it. An obvious next step from here would be to use these tools to make Lambda functions faster. If you think about the proportion of time in a SPARC job, often the data never leaves the driver. The results get written out to S3, they get written out to HDFS. And making RTD.map, RTD.filter, making these Lambda functions faster will have a much bigger impact on the performance of a PySpark job. Luckily, the same technology can be used to solve both problems. So it will be quite a bit of work, but I think we have I hope a reasonably clear path forward there. So if this is interesting technology, there's a lot of interest now in 2017 in improving SPARC's interface with native code or code that is outside of the SPARC Scala code base. So keep an eye on the SPARC Jira and get involved. If you can contribute to SPARC or Arrow or any of these projects, we'd love to have you involved. If even to kick the tires and use work in progress patches to help us understand the performance and things that we haven't accounted for would be super helpful. You can also help with writing documentation and kind of some of the other soft sides of open source projects, but equally just as important as writing the patches. So thanks, big thanks to the IBM crew and my colleagues at 2 Sigma for helping this work happen, and the other Arrow developers for getting to the point where we have a binary compatible implementation and for Python and Java. So thanks for coming to my talk.
Thank you, Wes. I think we have time only for one question. There are 2 mics on either side of the aisle. If you want to ask a question, do you mind walking up and speaking into it? And please make it very short because we only have a couple of minutes.
So we've actually also come across this situation. Like one of the things that we've seen was like flat buffers. I don't know if you've explored other formats that already do this kind of thing.
Yes, we use flat buffers in the Arrow metadata. So flat buffers give you, I would compare flat buffers to, as flat buffers are related to Arrow in the sense that protocol buffers are related to Parquet and column IO, kind of in Google parlance.
We got one more. Okay, well, give a big welcome and a hand to Wes for giving us a good talk on Apache Arrow and Python and SPARC. Thank you.